Here are a few examples of solving equations that have logarithms in them. Since we used logarithms to solve equations with exponentials, you might not be surprised to find that we'll use exponentials to solve equations that have logarithms. So here's our first example, log base 4 of x equals 3. And since the x is trapped inside of a logarithm, we somehow need to undo this logarithm. In other words, we need an inverse function for log base 4, but the inverse function for log base 4 is exponential base 4. In other words, we need to use both sides of this equation as an exponent on 4. Let me write this out a little bigger. So we get 4 to the log base 4 of x equals 4 to the third. Now on the right-hand side, we can just evaluate this. 4 to the third is 64, I think. And on the left-hand side, we have a composition of inverse functions. We have x on the inside. It's being put into log base 4. And that's being put into exponential base 4. So we have a composition of a logarithm base 4 and exponential base 4. Those two functions, since they're inverses, undo each other. And we're just left with the very inside, which is x. So x is 64. You can see, as long as in any equation where you just have a logarithm on one side, you can use this exponential trick to undo the logarithm and get at whatever's inside the logarithm. Let's look at a slightly more complicated example. Of course, in most examples that come from applications, you don't just have one logarithm, you have an equation with lots more stuff going on. So there is a piece that is a logarithm, but there's some other stuff laying around too. Well, we know if we can get the logarithm by itself, we will exponentiate to get rid of the logarithm. So before we worry about exponentiating, let's focus on isolating the part of the equation that has a logarithm in it. So we need to get this 3 out of the way. Let's subtract 3 from both sides. We get negative log base 5 of x plus 1 equals 5 minus 3 is 2. We don't quite have the logarithm part isolated because of this minus sign on the left. So we can multiply both sides by negative 1. On the left-hand side, that has the effect of getting rid of that minus sign. So log base 5 of x plus 1. And on the right-hand side, we have negative 2. All right, now finally we have the logarithm on the left isolated. So we can go ahead and use each side of the equation as an exponent for a base. It's easiest to use the base that matches the logarithm. So let's use each side of this equation as an exponent on 5. On the right-hand side, we get 5 to the minus second power, which is 1 over 5 squared, that's 1 over 25. And on the left-hand side, again, we have a log base 5 inside of an exponential base 5. And these undo each other. So we're just left with x plus 1. And then finally, finish solving for x. We can just subtract 1 from both sides. And we get x is 1 over 25 minus 1. That's negative 24 over 25. Okay, that's not so bad. So if your equation has one logarithm in it, just isolate that logarithm and then use the exponentiation trick to get rid of the logarithm. Of course, if your equation has more than one logarithm in it, that won't work. So let's look at this. Let's solve this equation for y. Log base 2 of y minus 1 minus log base 2 of y plus 1 equals 1. So it's maybe not obvious what to do here. It might be tempting to try to use some logarithm law to break up the subtraction that's inside of this logarithm, but if you look at all the logarithm laws, there isn't one that has a minus sign on the inside of the logarithm. So actually we can't break up this first logarithm. And by the same token, we can't break up the second logarithm either. But there is a logarithm law that can help us deal with a situation where the logarithms are subtracted. That's the product and the quotient and difference law for logarithms. And that property of logarithms does require that the exponents for the logarithms be the same, and in this case they are, so we kind of lucked out. So we can put these two logarithms together. We get log base 2 of, remember the positive one becomes the numerator, so y minus 1 over, and then the negative 1 becomes the denominator, so y plus 1. When I say positive and negative, I'm referring to the signs in front of the logarithms. Okay, and on the right-hand side, we get just 1. And now we're back to a situation we're more familiar with. We have a single logarithm. It's isolated, so we can proceed directly to undoing the logarithm by using an exponential. And since this log is base 2, we should use exponentiation base 2. So on the right-hand side, 2 to the first power, that's 2. And on the left-hand side, the log and the exponential undo each other. And we get y minus 1 over y plus 1. All right, so now we just need to finish solving this equation. This equation is sort of a classic case of linear over linear. We can solve this equation first by clearing the denominator. So on the left-hand side, the denominator simplifies away, and we get y minus 1. On the right-hand side, we can distribute that 2. We get 2y plus 2, and then move the y's to the right, and the constants to the left. So on the left-hand side, we get negative 1 minus 2. That's minus 3. On the right-hand side, 2y minus y, that's y. So y is negative 3. So if you are needing to solve an equation that has more than one logarithm, often you'll have to use the properties of logarithms to collapse the two different logarithms down into one, and then get rid of the logarithm using an exponential.